rules because it is our main finding. I will start with, to remind you about rank aggregation problem that we study. So suppose we have M candidates, or in the context of sports competitions, we call them athletes. And we have N individual strict rankings. It can be votes or competition protocols. So we denote them R1 to Rn. And here is an example of a profile. So we have 5 races and 3 candidates. And in the top position, we have the candidate that finished first in a race. So in first race, Amy finished first, Cass finished second, and Bob finished third. So we have a profile of all race results. So the problem here is how to find an aggregate weak ranking. So ties or indifference are allowed. So as input, we have only strict rankings, but as output, we have weak rankings. Applications, I will talk about sports competitions and maybe some words about elections. Of course, this problem arises in meta search engines, group recommender systems, and genetics and computational biology. And so I will talk about scoring rules in this context. So I want to remind you the main rules and to make you clear with our notations. So the most famous rule is plurality scoring rule. So this rule uses points from 1 and all other points are 0. How it works? So for our profile, we give 1 point each candidate at first position and 0 points for every other position. So in this example, for instance, score of Amy is 1 + 1 because Amy takes 2 first positions, and then all other scores are zeros because Amy takes second or third position for other races. So score of Amy is 2. Score of Bob is also 2 because Bob has 2 first positions. And score of Cass is 1 because Cass has only 1 first position. So here aggregate rankings is actually Amy tied with Bob, and they are both better than Cass. And so generalized plurality is just a refinement of plurality because it uses the same scores as plurality in the first round. But then in the second round, it uses scoring vector starting with 1, 1, and then all other scores 0. And so on in the last round, if it is needed, of course, all scores except last score are 1. So in our example, here we know that in first round, Amy has 2 points, Bob has 2 points, and Cass 1 point. It is first round points 1 vector. And we have a tie in first round between Amy and Bob. So by generalized plurality, we resolve these ties according to second position. So Amy has 2 second positions and Bob has no second position. So Amy has more scores than Bob in second round. So this is an example of generalized scoring rule where we have many rounds for tie breaking. And scoring rules are those generalized scoring rules that have only 1 round of tie breaking. And tie plurality is similar to plurality, but we start with last position, and so the points vector is 1, 1, 0. And generalized plurality is also similar to generalized plurality, but we start with anti-plurality vector. And in the case of ties, we use vector with 0, 0, and then all ones, and so on. And in the last round, it will be just plurality scoring vector. And maybe the most famous scoring rule is Bardar rule. It just uses points m-1 for the first position, m-2 for the second, and so on, and 0 points for the last position. In our example, it is very simple to find score of Amy is 2 scores here, 2 scores here, and 0 scores here, 1 score here, and 1 score here. So in total, we have 6 points, 6 total points for Amy. Bob has 4, Cass has 5, and aggregate ranking is Amy, Cass, Bob. in Bordeaux, we don't have any tie-breaking rounds next. And scoring rules. So what is scoring rules by definition? Scoring rule is a family of non-increasing vectors for each number of candidates. So for instance, we can have S1, S2, and so on. Sm, it's the scoring vector when we have m candidates. But possibly we could have in our sporting competition m-1 candidates. So scoring rule must define also maybe another, so not maybe, but just another scoring vector for m-1 candidates, and so on. So it's a family of scoring vectors for each number of candidates, k less or equal to m candidates. M candidates is maybe maximal possible number of candidates in an election. So Barda is just 2, 1, 0 for 3 candidates, and so on, m-1 to 0 points for m candidates. Plurality is always 1, 0, 0, and anti-plurality is always all ones, but only 0 points for the last position. So the main question in our paper is how should we choose a concrete vector of points for a particular application. And here a helpful disadvantage of scoring rules will help us. So for instance, consider a profile with 2 plus 3 plus 4 plus 2, so 11 races and 3 candidates. And as we see here in this profile, Amy takes 5 first positions here, 4 second positions here, and 2 last positions here. And Bob has a distribution of positions 4, 4, 3, which is definitely worse than positions of Amy. And Cass is the worst here according to the positional distribution. And of course, so it is clear that in this example, with any scoring vector S1, S2, S3, Amy will beat Bob and will beat Cass. Provided that, of course, this point vector is monotonically non-increasing. But we always claim it from scoring vectors. And suppose 5 years later, Cass was disqualified for doping. And after disqualification of Cass, who was the worst candidate in this profile, we have a new profile where actually Amy takes 5 first positions, but Bob takes 6 first positions. So according any points vector, but in this example, of course, any points vector is just 1, 0 without loss of generality, Bob will win this election. So here we see this disadvantage that is known as independence of irrelevant alternatives. And actually, the famous theorem of Arrow says that for 3 or more alternatives, a rank aggregation rule satisfies very weak property, weak unanimity, and independence of irrelevant alternatives, if and only if it is a dictatorial rule. So in this main context, we should live with dictatorship. Consider a real example. So in biathlon, in season 14-15, there were women's pursuit races. There were actually 7 races. And in that season, Kaisa Makarainen won the title. The scoring vector they used was 60 points for first positions, 54 points for second positions, 48 for free, and so on. It is on the slide. And her total points were 1 more than Domracheva's total points. So Glazirina was not a real contender. She took much less points than these 2 best competitors. But 4 years later, Glazirina was disqualified due to doping, and her results were annulled. Then she was cut out of every race protocol, and Domracheva got 1 additional point in race 2 because Glazirina was above Domracheva in that race. And after that, Domracheva now is the winner because these organizers use plurality scoring vector for tie breaking. So the number of first places of Domracheva was more than Makarainen's first places. And here we face with indivisibilities. So if we want independence of just winners or losers, then we should use Kemeny-Young method, but it is very complicated for real applications. And we also know from Fishburne's theorem that any scoring rule is vulnerable to this kind of paradox. So what to do next? Next, we can relax our independence condition, and we take it only for those candidates that are symmetric to other candidates. So it's independence of unanimous losers. So deleting loser in each race does not affect outcome. So loser in each race is a candidate that was the last in every race. So it definitely is the worst candidate in all profile. And also independence of unanimous winners claims that deleting winner in each race does not affect outcome. So I will show it by real example also, but semi-real example. So also in one of the seasons of biathlon, there was individual races. There were only 2 races in that season in this kind of discipline. And Gabriela Saukalo won both races. So she got 60 points for her first positions. And suppose hypothetically Saukalo was disqualified, as in our axiom, so Saukalo is a unanimous winner. And after her hypothetical disqualification, we'll have that Dobracheva now is the first, Kuzmina second, but Hildebrand and Skardina changed their positions. So here we have that real scoring vector that biathlon IBU World Cup uses is vulnerable to this kind of paradox. And this paradox is what we can fix. And few words about linear equivalence. So of course, if you have Borda rule, we can multiply the scores by 3, and it doesn't change aggregate ranking because aggregate ranking is just ordinal ranking. We can add or minus any number, and it also doesn't change aggregate ranking. So scoring vectors are defined with respect of linear equivalence. So if 2 vectors are linearly equivalent to one another, and they will give us the same ordinal ranking. And our main finding is that if a scoring rule satisfies independence of unanimous losers and independence of unanimous winners, if and only if there is a parameter p more than 0, such that this scoring vector is just 0 points for the last position, 1 point for the previous to last, then 1 plus p, then 1 plus p squared, and so on. And we define it also here because we can calculate this sum of geometric numbers, and then according to linear equivalence, without loss of generality, we can assume that for parameter p more than 1, we have just geometric sequence of scores. With p equal 1, we have exactly Borda scoring rule. And with p less than 1, we have inverse geometric scoring vector. So scoring vectors may be strictly concave, Borda, or strictly convex. Oh, sorry, strictly convex, Borda, and strictly concave. Sorry, does anybody hear me?
Yes.
Ah, thank you.
Yes.
Okay, so here we have also extreme cases in our class. If p goes to infinity, we have exactly generalized plurality, but we extend this class by generalized plurality because with p, when p goes to infinity, in fact, this scoring vector will be equivalent to generalized plurality for any fixed number of races. So this rule also known as middle count ranking, and actually in Formula 1 it was proposed in season 2009, but then in the last moment they changed it to another vector. Also, if p goes to 0, we have generalized anti-plurality. It can be important in some group recommended systems. Okay, so I have only 10 minutes. Okay, so what to do next? Our next question is, oh, we have a class and we have one parameter. Yeah, it is easy to choose one parameter than to choose all scoring vector. But how to choose this parameter? And then we apply axiomatic approach. And I will skip it today because I have only 10 minutes. So with axiomatic approach, when we pose some axiom, additional axiom, we will have a single rule. For instance, if you want to avoid some kind of paradox that just a geometric scoring rule is invulnerable to the winning a race paradox, it means that in some championships, you can win a championship without winning any race, as here. So Millinery won some races, Azuma won some races, but the champion won no race. But it is a champion. So to avoid this paradox, we must use generalized plurality. Or, of course, if we pose the famous majority winner criterion, we live with plurality. If we pose it to scoring rules, if we pose it to generalized scoring rules, we have only generalized plurality. So it's medal system. And similar result with majority loser criterion, which claims that majority loser will always rank last. We must use generalized anti-plurality. And also there is one axiom which is known as reversal symmetry. With this axiom, we will have Barda rule. So, but we were not happy with these results too much because real organizers, so they don't want to use only generalized plurality, Barda, or generalized anti-plurality. So, but axiomatic approach will give us exactly these extreme cases. So we apply empirical approach. So here I will focus in more detail because it is the most novel part of our paper. Suppose Xi is cardinal performance of an athlete in competition I. So it can be finishing time in a biathlon race. It can be strikes on a golf course. So it's some cardinal performance. And how to measure overall performance in all races, because we have n races, n competitions in the full championship. So here we use a well-known class of aggregation functions from this theory of aggregation functions. We denoted fb lambda of vector x. It's just, for instance, with parameter lambda equal 1, it's just sum of cardinal performances. So overall performance of a candidate can be just sum of his cardinal performances over all races. But also this class includes many other aggregation functions. With parameter lambda more than 1, it is just sum over all races, but lambda in power xi. And symmetrically with lambda less than 1, this sum is just minus lambda power xi. This is a well-known class because it satisfies a very desirable property. So if we have two candidates, one candidate have a distribution of his cardinal results x, another candidate has distribution of his cardinal results y. And suppose f lambda of x is more than f lambda of y. It means that x is better than y. And it is in fact if and only if f lambda of f plus f lambda of x plus any constant c is more than f lambda of y plus any constant c. So in the sporting context, it means that it doesn't matter that we calculate finishing time as a log from the world record or from 0 or from any other fixed, so from 1 minute and so on. And actually, we have another desirable property here, is just if we multiply these vectors x and y to some constant c, In the sporting concept, it means that it doesn't matter whether we count our finishing time in seconds or in minutes. And the result will be the same, provided that the organizer will not forget to adjust his parameter lambda. And next, we exploit a very general result known in the theory, how to find optimal scoring rules. So here I just redenoted UI is cardinal qualities in competition I. So UI1.
5 more minutes.
Yeah, okay. UI1 is just cardinal quality of athlete 1 in race I. UIM is cardinal quality of athlete M in race I. And then we reorder it is in non-decreasing order. So, and the famous theorem says that with some rather weak assumptions, if we consider scores Sj, scoring vector, where Sj is just is expectation of this J order statistics of these cardinal qualities, then if we apply the scoring vector in the scoring rule, the winner actually will be the athlete with the highest expected overall quality. So in this sense, this scoring vector is optimal. And then we apply this theorem to real examples, and found that, for instance, in biathlon competitions, so optimal is violet, so optimal scoring vector is here, and red is what these organizers actually use. So we see that they actually use scoring vector very close to optimal. Geometric works here not so well, but not so bad. And for instance, in another example with Diamond League 100-meter sprint, the organizers use Barda scoring vector, and optimal vector is violet. It is very close to Barda, and actually geometric is also the closest geometric scoring vector to this is also have parameter close to Barda. And if an organizer wants to increase suspense, so to encourage competitors to be more risky, it could choose lambda more than 1. But in this, then the organizers must use so optimal scores are very close to geometric scores. But it is not the case always. For instance, in golf, so we took PGA Tour, and actually PGA Tour optimal lambda, if we take lambda 1.4, it's more than 1, so it encourages risky behavior in these golf events. Then we see that this optimal is violet, it's here. It is very close to real PGA Tour money sequences that they use and PGA Tour scoring vectors that they use. So it's all three are almost the same. But geometric scores here works not so well. They do not approximate these three. So geometric are not here. And so we can conclude that so our weak axioms of independence give us convex rules, concave rules, popular rules, Barda, plurality, anti-plurality, only 1 degree of freedom for real organizers, and we took new concretizations of Barda, generalized plurality, and generalized anti-plurality, and when we tried to combine avoiding paradoxes with optimizing scores, so maximizing expected overall quality of athletes, we face with inevitable trade-off. Thank you very much.
Thank you very much for an excellent presentation. That was really good, and I wish sports authorities could use those things much more than they do it now. Okay. Now I have a question before I give the microphone to other people. When you said optimal, I'm sorry, probably I missed it. What did you mean by optimal for athletes, for example, or for organizer?
It was optimal for organizers. It is optimal in the sense of the theorem that if organizers counts overall quality by this formula, so the organizer only knows ordinal ranking. Organizer doesn't know cardinal rank. I mean, by organizer I mean that they count only ordinal ranking. Yeah. And so if you know only ordinal ranking, then you, using conditional mathematical expectation, you can recalculate their expectation of their overall quality. Yeah, I understand the question. So the input is ordinal ranking. Yeah. And this theorem says that you should use exactly these scoring vectors. Yeah, but of course, in many competitions, organizers know cardinal rankings. So they could use exactly their formula of overall quality.
I would even say not only know, but care much more about the cardinal than the ordinal. And I don't know if you know, but in biathlon, for example, those who finish last in mass start, they really don't care, and which harms the competition. So anyway. Okay, any other questions?
Yes, Alexei, thank you so much for this presentation. I have a question about the trade-off between while designing a scoring system and between designing the system of prizes, the distribution of money. Okay, so it seems that in some cases, at least these two systems are very different. Is there some consistency between between these two problems? I mean, can we identify some good properties so that these two systems of scores and prizes are consistent in some sense?
Yeah, it will be the next step of our research. So it doesn't exist in the literature, and so we will work on it. We have some ideas, and so I have no time to explain them. But yes, it is actually the question, because, for instance, in biathlon, on the slide, so I didn't say it, but it was on the slides that so optimal scores are very close to their real scores that they use. But their prize money distribution was very close to geometric distribution. So it is very strange that you have incentives. So according to money, you have one incentives, and according to scores, you have another incentives, very different, because optimal scores are very different of geometric scores in the case of biathlon. And it will be the next question, yeah, the next scientific question.
I must tell you in that regard that I spoke with Ole Dalin, the president of the International Biathlon Union, exactly about this. I told him, look at your point distribution and look at your money distribution. Какая связь? And he didn't know what to answer.
Да, можно по-русски. Алекс и Дмитрий, я вам первым отправлю, вот как мы буквально вчера дописывали, вот буквально через пару дней допишем полный текст, он уже 50 страниц. Мы первым вам отправим текст, и вот, да, следующий вопрос будет вот действительно, почему они так делают. Там это всплывает, но мы не можем в 50 страниц туда уместить это, и это будет следующий вопрос, да.
Ну, я думаю, тут может быть какая-то, ну, отправьте, а там мы будем про другое еще думать. Я уже...
Да.
Видите, как хорошо иметь такие конференции, когда можно, когда идеи приходят. Ну, то есть это идея между деньгами и points, она стара, но еще когда есть данные по поводу перформанса, то это вообще может быть круто. Окей.
Можно я немножко, одну минуту? Вот этот президент, он сам признает эту проблему?
когда я ему послал этот имейл, то есть я ему послал, вот, и он очень заинтересовался, потому что я ему послал связь между эффортом и очками, что она где-то, то есть есть связь. А потом, ой, как интересно, а вот мы сейчас деньги вот по-другому. Я ему послал, говорю, ну нету связи. Он не ответил.
Ага. Ну, надеюсь, да, мы его как-нибудь убедим. Хорошо, спасибо.
So I will present our work on spotting behavior, which was developed with Marina Sandomirskaya, who's sharing the screen. So I would like to start with the outlining type of tournaments we were focusing on, and it is the type of knockout tournaments. And you can see the example of double elimination tournaments for 4 players, and can see on the picture that it consists of 6 rounds, while if we will look on the single elimination tournament, there will be only 3 games. So we will compare these tournaments. So can you go to the next slide? It is quite obvious that more resources are spending in sports theater, but the more resources are invested in sport, the more problem we can face with. For example, at London Olympiads, 8 badminton players was disqualified because their unsportive behavior. The rules of the tournament slightly changed at that time, and the winner of each match would face with the strongest player, and that is why everybody has no stimulus to win this match, because otherwise he will face with the weakest player, and it would be easy to win whole tournament. It was a problem, and judge gave them just a red card, but they still didn't play well, and so they just were disqualified. And it was the problem. Moreover, not only in sports, we can use such type of tournaments also in cyber sports and at labor market. And the main question is how we can avoid such a problem when players put 0 efforts to win in such type of tournaments. So our goals were make something like guidelines for tournament designers, and show how difference in straight level influence these total efforts, which can be approximation of entertainment level, which tournament organizer maximize. So can you go to the next slide? I will outline 3 main papers related to this topic, and the first one is Lizard and Rosen. They were pioneer in this tournament theory, but they focus only on 2 identical players. So they have only 1 match, but also they take stochastic components, because they develop this tournament theory in labor market. And the main results, which is important from their paper, is that players' efforts, total effort, increases if the difference in prices increases, and also that players care not about absolute price, but the difference in prices. Can you go? Okay. One other paper developed by Huang is important because he was the first who focused on double elimination tournament, but still he just worked with tournaments with 4 identical players. And some other assumptions which he made is the distribution of prices and Staller probability function. The main results is that it is more profitable to put all money at the top price, give all money for the first place, and that it is for both type of tournaments, and the entertainment for double elimination tournaments is less than for single elimination tournaments. Can you go to the next slide? And one other paper focus on the different players, different type of players, but still for tournaments of 4 players, they use all-pay auction for probability, but they compare different goal function for designer of the tournament, and they get some results for different type of these goals. But we will we focus on the different players for 2 type of tournaments and for the maximization of total efforts instead of some other goals which we can imagine. Yeah, can you go to the next slide? So we design probability as an all-pay auction. You can see it on the slide by number 1, and created expected payoff in such way that V is expected payoff for player I at the stage C, and W, it is the price which player gets if he eliminated at this stage C. So if he loses, he just take money for which he can get from this round and pay all costs for this match. So this expected payoff is created for each match in the tournament, and it is obviously different for different players. Can you go to the next slide? So we get some types of equilibrium, like 2 extreme cases when all players, 2 players in a match puts 0 efforts, the lowest effort which we can imagine, and the other type when players put the highest efforts, both players put the efforts, which is denoted by E bar, but we have something in the middle when players play mixed strategies for some constraints, on the cost functions and price difference in prices, and the main results which we get from mixed strategies is that it depends on the parameters of the model, and also a strong player may lose because of their overconfidence when he meets with the weak player. He just wants to put lower effort because he just confident in the straight, but the weak player decided to put all the maximum effort to this match, and in this case strong player may lose because of this overconfidence. And also for mixed strategies, it is true that the higher the difference in strength between players, the lower total efforts we get, because if the strongest player meets the weakest player, the weakest player just decided to skip this match, not to put high efforts, and that is why the strongest player also reduced the effort because he would like to minimize their costs when the probability of winning is still constant. So can you go to the next slide? And then we just simplify our model a little bit to get more general results for the whole tournament. Like we decided to put whole price to the first place, as Huang proved in his work, and also reduce the number of possible strategies to 3 strategies. We can see that these different types of equilibrium, which I already described, depends on the price size and cost function. And we are interested in 2 extreme cases when total efforts is minimized and total efforts are maximized, and we get some constraints on it. For example, if the total price, which we assumed go to the winner of the tournament, is less than 2 in the power of t-1 multiplied by costs of the minimal level of efforts of the weakest player, then all players in this tournament will play they will put 0 efforts, so to avoid this case, the designer of the tournament should increase this price higher than this number on the right part. On the other hand, we get the condition on the maximum total effort. So it should be higher than this expression and the number 4 on the left part. I also should outline that T is the number of games in some tournaments, and C is a cost function in these points of maximum efforts. So in this case, all players put their highest effort because the price is high enough to stimulate them to play such equilibrium. Okay, can you go to the next slide? And we compared these 2 types of tournaments for 4 players and for case of maximum total efforts to decide which tournament is more profitable, and get these conditions. Like for the single mission tournaments, we get less maximum total efforts than for double mission tournaments. For double mission tournaments, it is twice times higher. But on the other hand, we can see that the costs of these tournaments would be higher because to get this maximum total effort, we should pay more to the winner, approximately 10 times more for such case. And that is why we can say that for double mission tournaments, total efforts is higher, but it is costly, and it is just trade-off between these two conditions. Okay, can you go to the conclusion slide? So we find this level W min and W max, which outline 2 extreme cases of the tournaments to get some different types of equilibria, and just get some intermediate results for some mixed strategies in which showed that the strongest player can also lose because of their overconfidence. And can you go to the last slide? Thank you. If you have any questions, please ask.
Thank you very much. It was very interesting. And as someone who's coming from the old base school and wrote several papers with an Arcel, I really liked to see this Groh et al. Economic theory paper. Very nice. I remember when I did my PhD, I kind of, oh, that's the paper. I'm wondering, so probably in the paper you have many references, but there is one paper by Deck and Kimbrough in GIBO in 2015. You cite there the economic letters paper. But Deck and Kimbrough, they have a paper, experimental, but first they had the equilibrium there, single and double elimination, all pay tournaments. So it would be nice to see what is your contribution beyond what they did. So just as a note.
Okay, thank you.
Okay.
We will see.
I think we must look more carefully at this paper, yes, because probably it seems to us that it is more experimental, yes, than theoretical, but we should check it. Thank you for this link, yes. And can I make some comments, yes, about it? Okay. A short comment, yes, just to clarify what is our main point, yes, why do we need this double elimination setting, yes, because we have a trade-off, yes, as usual, when you deal with single elimination tournament and unequal players, you can face a situation with very unhappy initial seeding, yes, for example, two strongest players meet at the first round, and this is very bad for the performance of the tournament, yes, because one of them need to be excluded. That's why double elimination tournament allows to overcome this difficulty, yes, but it occurs that itself, the structure of double elimination allows some other problems, yes, like the different kinds of unsporting strategical behavior, yes, of lowering the efforts, and again, organizers doesn't like it, yes, that's why here we want to understand how costly is to exclude this situation, how costly is to make the largest performance even in the very bad initial seeding, yes, because we can exclude this bad situation, but we must pay, yes. So there is a complicated scene how to do this, yes. This is not about the result, this is about motivation, some parts.
By the way, may I add another motivation that you can add it. The next Olympics, if they take place in Tokyo, they have baseball tournament. And baseball tour, I recommend you to look at because this is also double elimination, the first time in the Olympics, I think. Okay. Actually, judo also double elimination from a quarterfinal. Okay. I have paper on judo, so how could I forget? But baseball, this is the one that really you can motivate it with this, and also judo.
Oh, thank you. Yeah, it's nice. Thank you.
It's always the editors, they like to see, okay, math, but reality. Okay, there is a reality. And believe me, as someone who came from game theory, I struggled a lot with, to link it to reality.
Thank you, Alexander.
Any more questions?
Maybe a question from me. Well, how this setting can be extended to the tournament with many players? Because, well, there are many different ways to introduce additional tournaments in that case, and it seems to me that the combinatorics of the structure is very rich, and well, if the calculations are more or less simple in case of 4 players, I'm not sure that these results can be just extended to the multiple players case. Can you please comment on that?
Can I share my idea how we can deal with these many numbers of players? So in double elimination tournaments, for example, we can divide tournaments in some section, for example, and start with the final section for when only 4 players are left in the tournament, and it looks like the tournaments we have analyzed, but adding new section, just extended tournaments, we can look at these big tournaments as the chain of tournaments, because players compete not for the final prize, but for participation in this small tournament for 4 players.
Okay, thank you.
But may I help you with this question to you guys? First of all, again, you can use the examples I gave you, but the second one is that 4 players is a very common tournament design. So in that regard, you can answer. And obviously, Dmitry has an excellent question here. That's the usual question that referees ask. Okay, but how can you generalize it? Oh, come on, with 4 players, it was tough to solve. What do you want? But this is a decent question that you will probably face.
I also face all those difficult questions from referees. So.
Yeah. So we know where it comes from.
No, up to some limit, we need to use the recursive structure of the next round, yes, to split into 2 parts, so add round by round, yes. But of course, at some point, we need to come to some, probably to some simulations, yes, because up to some limit, it will be analytical results, but then only simulations, of course. So, or it will be a lot of simplification about the strengths of the participants. For example, only 2 groups, yes, strong and weak one, yes. So anyway, we need, of course, simplification for very long tournaments. So, thank you.
Okay. So thank you very much for having me in this nice conference where I can show off my skills in Russian. So this is a joint paper with Felix Otto and Tim Pavlovsky from the University of Tübingen, and it's called Nationalistic Bias Among International Experts, Evidence from Professional Ski Jumping. And it's always nice when Israeli guy talks to all those winter nations about winter sports. I have papers on biathlon now, on ski jumping, and to be honest, I can't really even ski. So anyway, but this is not really about ski jumping. So we are talking about in-group favoritism. And this is based on division of people into different groups according to some rule. And unfortunately, this in-group favoritism is a very well-established phenomenon that just refuses to disappear, even in 2021. Now, there was a nice study by Efferson and colleagues in 2008 in Science, and they showed that, you know, if you have people with different figures on shirts, that was enough to divide people into different groups, like people with triangles and people with circles. They were together, and then if they saw somebody with different sign on the shirt, that was already enough to create in-group favoritism. So it's a very, like, this feature of favoritism is a very strong feature within us. Now let's go to some sports studies that showed the same. So there was a very nice paper by Price and Wolfers in QGE. They found that NBA players had fewer fouls called against them when they race matches that of the refereeing crew. So that was a big scandal after this. I will come back to this study, but black referees had more fouls against white players, and white referees had more fouls against black players. More or less in the same way, Pop and Pop in 2015 showed that referees favor their compatriot players by assigning them more beneficial calls in UEFA Champions League games. For example, if a Russian referee referees a game of Atalanta where there is a Russian player, he will give more fouls in favor of Atalanta. Yeah, that's the only team, if I remember correctly, in Champions League with a Russian player. And recently, me and my co-authors from Switzerland, we studied games in Swiss soccer, and we showed that referees, you know, in Switzerland, there are 3 or 4 languages for linguistic areas. So we found that referees from one linguistic area assigned significantly more yellow cards against teams from a different linguistic area. So, and why sports is a good setting? Because everything is observable. You just ask the right question. Now, actually, we built on efforts of Eric Zitzewitz, who published in 2006 paper with exactly the same research question, in exactly the same research settings, so in professional ski jumping. So he found that referees assigned significantly higher scores to their compatriots, okay? And you know, ski jumping, just several words for those of you who don't know, it's they just ski and then they jump. And it's a combination of scores, length of the jump, and style points of reference. Now, there was several follow-up studies after Zicevich. So first of all, he found the same story in figure skating, that referees assigned significantly higher scores to their compatriots in figure skating. And in 2018, Sandberg published a paper in Economic Journal, and she found a similar result in dressage competitions in equestrian with horses. So what are we doing? So first of all, we want to retest different nationalistic related biases almost 15 years after the initial study of Zicevich. Okay? So we go back to this setting and we want to see whether it still remains. Why is it important? So first of all, awareness of a problem is of a great value, because you need really good feedback to judges to reduce this bias. And as evidence, you remember the paper on basketball that referees assigned more fouls against players from a different race. There was a big scandal in news. And then Pope et al. And colleagues in 2018, they published a paper in Management Science. They did a follow-up study, did exactly the same thing. And then they found that this favoritism, this rational favoritism, completely disappeared after widespread coverage in newspapers. So that follow-up study showed that racial bias disappeared, and you just need a good feedback, maybe some negative reactions, but then people kind of work on it and it improves. Second, we contribute to the growing debate, and in fact, I think this is the main contribution of this paper. There is big crisis, big replication crisis in science. So for example, in 2015, open science collaboration, like 100 co-authors in this study, they could replicate the results of only 36 out of 100 experiments that were published in top academic journals. Moreover, there is another study in 2018, they gave a football-related data to 29 scientific groups. And for the same data set, they showed a high variance in the results. Okay? So, and they highlighted the importance of crowdsourced research. It can balance discussions, validate scientific findings, and better inform policymakers. So replication crisis is a big crisis in science these days. And for example, in business and economics, Ioannidis and Dokoliagos, they discussed the empirical evidence on the lack of a robust reproducibility culture in economics and business research. And it's an important scientific task to try to replicate original findings. As someone who referees papers and as associate editor in one of the journals, I must say that yes, referees sometimes they say, well, but somebody has already done it. What is your contribution? So an answer to this question could be, we want to see whether replication works. And usually it's not in game theoretical fields because, well, 2 + 2 is 4. What else can you do, right? More or less. But in empirical studies, this is very important. Our third contribution. Judges may use strategic voting. So let's say if I'm from Norway and there is a Russian referee, I will assign higher or lower grades to Russian athletes, only because I have a colleague in the judging panel from this country. So this is what we call strategic voting. So on the one hand, Zicevich, who coined this term compensating bias, found that ski jumping judges assigned lower scores to jumpers of the same nationality as one of the judges in the panel. On the other hand, in figure skating and in dressage, there was an opposite result. So actually, they do assign higher scores to somebody whose compatriot is in the judging panel. So the evidence is mixed, so we contribute here as well. So just, I think I will skip the ski jumping settings. I think most of you know. They just jump, they calculate distance plus scores of referees. That's more or less what you need to know. Okay, so what we did with regard to data, we collected data from the official website of this ski jumping, from all men's World Cups, Nordic World Ski Championships, and Olympic Games for the seasons between 2010 to 2017. So I don't like to take several competitions from here and several competitions from there. I just cut the whole period of time, and everything that was there, I take it. Now, we had 203 competitions in 14 countries, 268 athletes. So we had information on more than 15,000 jumps, which totaling to 76,000 different jump evaluations, because every jump is evaluated by 5 judges. So pretty nice data set, I would say. And this is descriptive statistics. So we can see that style points, when there is a compatriot jumper, the style point is a bit higher than when there is a non-compatriot jumper. We also see that home event, when there is a compatriot, we have 30% compared to 12%. So those things should be taken into account in any empirical analysis, because by default, a home judge must present in the judging panel. So if the competition is in Russia, there must be a Russian referee. There must not be a Norwegian referee, but Russian, yes. Okay. And the jumping distance, we can also see some difference. So what we are doing, what is our strategy in terms of estimation? So just to compare the means of style points will yield biased and inconsistent result, because jumpers' unobserved ability is likely to affect his performance and also the decision making of the judges. In addition, it is possible that jumpers whose compatriot is on the panel have on average a higher quality, as both the jumper and the judge come from nations where ski jumping is more popular. For example, if we take a jumper from England, I don't know if you saw the movie Flying Eagle or something like this about ski jumping. So there was an English jumper. He did not have a compatriot judge, but he received significantly lower scores, not because he did not have a compatriot, because he's simply not a good jumper. But Norwegian jumpers who have a compatriot, they probably are good jumpers. That's why they get better points. So it's not enough just to compare the means. Okay, but what is happening is that our data allows us to compare within the same jump the style points of a compatriot judge with the style points of non-compatriot judges. So everything is taken into account. We will use, so here you can see we are using jump fixed effects. Everything that was constant within jump, where I am, who I am, everything is perfectly taken into account. So we use this fixed effect model, and we want to estimate this alpha 1. How compatriot jumper, because we have 4 non-compatriot and 1 compatriot, or we have 5 non-compatriot, for example. Now, beyond the issue of a nationalistic bias, another concern is that there is this strategic voting. But in that case, we cannot use jump fixed effects, because the composition of the judges is fixed within each jump. So for example, if I am from Norway and there is a Russian jumper, I am saying that, okay, there is a jumper whose compatriot is in the panel, and also the other says the same, and also the other says the same. So jump fixed effects deletes all those things. I cannot use it. Instead, I will try to use as many as possible observable things and also unobservable. So we use, so this is our main, do you see my mouse, the arrow?
Yes.
Yeah. So we care, of course, this is nationalistic bias, compatriot jumper, and this is strategic bias, compatriot on panel. And we also use judge per season fixed effects. We use a competition round fixed effects. So everything we control for many possible things. We also use home advantage thing, the length of the jump, because length of the jump we must use because we don't use jump fixed effects. So then if we will not use length of the jump, we miss something, okay? Okay, so these are the results. We can see that by using jump fixed effects, compatriot jumper receives 0.9 more points. A jumper receives 0.9 points more from compatriot jumper than from non-compatriot jumper. And this is like the strongest one. This is controls for jump fixed effects. Now, when we want to use compatriot on panel, we have to relax these jump fixed effects, but then instead use some other fixed effects. And we see that compatriot on, first of all, the compatriot jumper remains more or less the same, very significant, positive. And compatriot on panel, the jumper whose compatriot is on panel receives close to 0.2 points more, not entirely significant at conventional levels. But when we use home event, which other papers did not use, by the way, and I was very much surprised as someone who's coming from sports economics literature, I said, well, you must control for home advantage. So when we control for home advantage, which also has an effect on style points, we see that compatriot on panel is basically zero, no effect. But compatriot jumper remains very strong. And then we showed actually what can explain that there is home advantage, and people, in fact, they perform better at home, and we use length of jump as an outcome variable, and we really see that at home they jump more. So they just to see that really home variable is very important and we have to include it, which other papers didn't do. Then we said, you know what? Maybe there is some maybe there are some outliers, and this is why the result is driven. So we checked for every judge, whether he assigned more or less higher or lower scores to his compatriot, and we see that 77% of judges show a positive nationalistic bias, with almost half of them are positive and statistically significant, and only 2.5% of judges show a negative and statistically significant nationalistic bias. So no outliers. We can see that this is a very strong result with regard to all the judges, or more or less all the judges. Now we'll talk whether all the judges or not really all the judges. And compensating bias, we found zero effect, and indeed we find that 55% have positive compensating bias with only 8% significant. The rest, 45%, show negative. So it's really more or less no, we can't find some effect that there is, that if there is a Russian referee, I as a Norwegian will give higher or lower scores to the Russian jumper after controlling for all the reasonable things. Then we said, okay, let's see some effect heterogeneity. Maybe the bias differs between different competitions and between different rounds. In fact, we see that it doesn't matter whether this is round first, round one, or round two, or only top 30 of the round one, or this is normal heels, or whatever. So we cut the data and we see that the nationalistic bias, according to which judges assign significantly higher scores to their compatriots, this is more or less the same. The only difference is the Olympic Games with really 0.21 higher bias. We cannot really conclude anything from this because we only had one Olympic Games in our data set, which was in Sochi, but this is what we find. Anyway, when we run interaction analysis, like regression with interaction terms, we find that Olympic Games is not significantly different from others, but it is different. It is different. We cannot deny that this is not. Then we took a look on this country-specific variation of nationalistic bias. And unfortunately for Russia, Russian judges assigned significant, I hope I'm not getting you into troubles now with all these new laws about, yeah, but this is purely scientific one. I can give the data, you can check it. So Russian judges, they assigned the average bias of Russian judges is the highest in the data. And the only two countries that have zero bias in terms of statistical significance and in terms of economic significance, these are Finnish and Norwegian ones. So in Norway, yeah, they really like the study. I guess in Russia they liked it a bit less, but this is how it is. So Norwegian and Finnish have zero bias. Russians, Polish, Czech, they have more bias. And then I said, because I have another paper on corruption perceptions index, straight away I said, okay, let's see the correlation between the bias, the size of the bias, and corruption index. And we can see here that there is a pretty significant, you see the line, the slope. I can tell you from regression analysis, this is very significant. So here we can see that's a nice figure that we learned to do from other paper. So here we can see also referees, also countries, also the number of times the refereed. A bit not clear from the beginning, but when you look at it very carefully, this is a very nice figure. So the circles show the judge-specific nationalistic bias. The size of the circles is relative to the number of observations for each judge in the data. So you probably, yeah, there is something. Russia, yeah. But then we said, one may say, look, Alex, you spoke about this thing in science that we cannot replicate findings. So let's compare your findings with the findings of other papers. And this is what we did. So a comparative view of nationalistic bias between our study and studies of Zicevits, ski jumping, figure skating, and dressage. And we can see that, well, our results are lower than the bias in the previous ski jumping, in figure skating, and they are kind of more or less the same as in dressage, although not exactly the same. So why is this? Why we are so different from the other ski jumping paper? So, and here it comes to data. Because Zicevits only used data on the year 2002, which was the Olympic year. And in both studies, the nationalistic bias in the Olympic Games is the highest. 0.26 in Zicevits and 0.22 in our study. I remind you, that's the one. 0.22 in our study. So Olympic Games, they really differ. But in our case, the share of the Olympic Games from all the competitions, from all the data, is only 1% of the overall number of observations. But it is 13% in Zicevits. So the Olympic Games, they take the whole result up. So you have to have really representative data set. Olympic Games take place only once in 4 years. So its share is not 13%. And by the way, the dressage paper don't use Olympic Games. Now, when comparing our finding to figure skating, it should be noted that ice dancing accounts for 1/3 of the data on figure skating in Zicevits. And then, as someone who was born in the Soviet Union, I remember all those. My wife still likes this so-called sport. Okay, so what they say is the following: biases are larger where scoring is more subjective, as it is for ice dancing, where skaters do not have as many mandatory deductions for falls and for artistic impression, as opposed to technical merit scores. So, for example, in technical, like women or men, or there is ice dancing and there is pairs, they jump, they can fall, and then someone like me, who has no clue in figure skating, I can understand, okay, there was a fall, probably did not perform that well. But in ice dancing, they don't fall, they perform. I was in 2007 in European Championship in figure skating. Well, we had tickets to ice dancing, and they all perform exactly the same. So that was, and I couldn't really understand why those get more points, why those get less points, but I'm not a professional, so I shouldn't. But this is what Zicevits tried. And in fact, the nationalistic bias found by Zicevits for ice dancing is 33% higher than the one for non-ice dancing disciplines. And this is in line with different other studies that show that when there is a room for interpretation, there are much more biases. And this is exactly what's happening here. Now let's go to compensating bias. Some papers found that there is compensating bias, that like strategic voting, like in figure skating and dressage, but we didn't find. We find zero effect. So without home advantage, this is a bit high, but when you control for home advantage, you find zero effect. Those papers did not control for home advantage, first of all, and you see that the bias becomes zero because they simply perform better at home. So you have to control for this. And there are also, so another possible reason why we observe positive reciprocation biases in figure skating and dressage is that they relate to different institutional settings that relate to truncation and exposure to scores of sports in the sport. So for example, in figure skating, up to 2016, I think, starting from 2002 to 2016, there was anonymity, which is really bad. Like when I heard this, I said, how come? What is anonymity? Every judge could give any score he wants, but no one could identify the judge and the scorer. So I could, and this is a very nice setting to be involved in strategic voting, because nobody knows what I do. This is one. And second, the scores are randomly truncated. Unlike in ski jumping, where the highest and the lowest score are truncated, here in figure skating, I can give the highest score possible, and there is a very high probability that my score will not be truncated because they truncate it randomly. They remove the scores randomly. I was very much surprised why it's working like that. And in dressage, panel members must have an evaluation meeting after the competition if the scores for a performance differ by more than 5% among the judges. So it is possible, I don't know if this is really the case, but this is possible that experienced dressage judges anticipate this nationalistic bias, and then they act accordingly because they don't want to have this discussion about this 5% thing. So for example, they can give better and biased scores to ensure consistency, for example. So this is different than ski jumping. They truncate the highest and the lowest. There is no such thing of 5% rule. So this could also play a role in the different results. So let's conclude. So our results indicate that well-trained professional experts, and I like this, professional experts, so many biases and they're still experts. So they are prone to nationalistic bias even almost 15 years after that bias was first illustrated in ski jumping. This suggests that the in-group favoritism is a very strong feature of human behavior and that the ski jumping authorities should exert more efforts to mitigate it. Maybe less efforts in Norway, but much more effort in other countries. So our results were obtained from fully observable sports competition. Therefore, such an in-group favoritism may even be stronger in less transparent settings. So imagine here everything is observable. So some Alex like this can come and do this study and say, oh, Russian referees, they are biased. So you have to be careful. But imagine now what's happening in other fields, in other settings that nobody knows what's going on there. I'm just raising a question. I don't really know. I imagine what's going on in other settings. But, so favoritism may even be more extreme during the times when the entire humanity faces difficulties such as coronavirus, where the immediate and natural desire is to protect in-group members. For example, some countries, they want first to be vaccinated in their countries and then to export the vaccination to other countries. But this is what it is. Now, another thing, unlike previous studies, we find no evidence for strategic voting, which is a good thing. So this discrepancy can be explained by different approaches of how to deal with home advantage in other studies and some differences in institutional settings. And last thing, we call for future research to investigate nationalistic favoritism in other settings to bring to a higher awareness of this really, really primitive human instinct that unfortunately has not disappeared yet. And if to be a bit pessimistic, it will not disappear for years to come. But based on what the NBA papers showed, that if you make a big deal out of this, there is an awareness and people will think twice before doing this thing. So thank you very much.
Thank you, Alex. for this interesting presentation. Well, you know, now even European UEFA reference, for example, was Soviet bloc to matches with teams from other post-Soviet countries. So it seems that worldwide this topic well is regarded as an important, but it seems that this effect of bias sometimes is lowering in some sports, maybe not in ski jumping, but in some other sports. We will see what will happen next. Now, questions, please.
Yes, yes.
I have a question, small questions. Probably if you imagine, yes, some experiment that all players, all sportsmen are anonymous, yes. This, for example, they cannot use some symbolic of their countries and so on, such that such factors must be at least excluded from the the decisions of judges, yes, or probably not so sharp, yes. But in this case, you will have some loss in performance from the organizers, yes, because they can earn a lot on this national symbolic, yes, and national competition. So can you estimate what effect is more harmful, the losses from this lack on national identification, or this corresponding bias of the judges? Yes, because probably can you compare or identify it from data? Yes, compare different types of
This is a very good point because there are many studies that show that anonymization, like in orchestras, that when they started to have to blind auditions in orchestras, they hired significantly more women, for example. And there are several other studies that I don't remember now, that when it's anonymous, it's the best. But why to go there? Let's just remove those referees and have the longest jump, the best result. It's much more simpler, I would think. Yeah. But with regard to your question, I don't know how to. Of course, there is a trade-off. I don't know how to do it. By the way, just one remark. When I sent this paper, it was still under review. Several weeks ago, it was accepted to Scandinavian Journal of Economics. So I apologize for presenting.
Congratulations! Congratulations!
Yes, thank you very much. It was torture, but okay.
But a very good outlet.
Yeah, thank you.
Okay.
Can I ask a question?
Yeah.
Maybe I don't understand, but do you look at the distribution of places? So influence this nationalistic biases to the place of athletes.
What do you mean by place?
First, second place.
You see, you mean, yeah, we could have done it. We didn't do it. We could have done it, like to see whether the bias is stronger for the best, or if somebody number 20, then it doesn't matter. That's what you...
Yes, and influence that if there is a bias, player would be the second, but with the bias, it become first.
Yeah, but on the other hand, in fact, we did control for this. Once you use jump fixed effects, it's there, isn't it? Like everything that is constant within the jump. Or you mean, so let's say it should be there.
Можно я сейчас перейду, чтобы точнее выразить мысль. Я имею в виду в том, что влияет ли вот этот вот bias на то, какое место в итоге занял спортсмен. То есть,
наверное, влияет ли место?
Нет, вот именно наоборот, в том, что является ли этот bias определяющим в местах. То есть
мы не сделали. Мы не сделали, но какая-то финская самая большая газета, они напечатали про эту статью. Там прям взрыв был пару месяцев назад, мы это дали журналистам, и прям вообще было. И вот одна финская газета, они даже сделали лучше, чем мы, они там написали, что вот какой-то был спортсмен, и его финский судья засудил своего же. Ну, как бы я не удивлен результатами. И он должен был, и он его засудил так, что тот не побил мировой рекорд по количеству раз, что он выигрывал подряд. Вот как бы вот такое вот было. Ну не, мы не проверили, но это хорошая, в общем, хорошая идея.
Anti-bias эффект.
Нет, это называется outgroup bias.
Outgroup bias. Okay.
Да.